Hi! Sound is a weird soup and your brain most likely lies to you. Let me show you how. We will start with a sound sample. Ideally you should wear IEMs or earbuds. Headphones are fine too, but every kind of loudspeaker will result in a different effect. I will explain it later. Ready? Go! What did you hear? Most likely you heard a tone that wobbled or got very fast, louder and quieter. But that's not what your headphones played. Go back and listen again, but with only one speaker in your ear. Jump back now. Did you hear the difference? If you only listen with one ear, the sound seems to be a continuous sine wave. But if you listen with both ears, your brain starts to make up this wobble. Now let us figure out where this comes from. In short, your brain is inventing a beat frequency. And this video will tell you exactly what a beat frequency is and why it is fascinating that your brain can just make it up. We are in the void again. Around us is nothing except air. This plane shows us the pressure at each location. We will start with a single speaker. It creates pressure waves that travel in a circular pattern away from the sound source. The strength of the waves and thereby the loudness gets lower the farther away you are from the speaker. For simplicity we will draw this on only one axis. And we see that the wave always stays below this envelope. Now we will add a second speaker, and both start to emit sound waves of the same frequency. Since waves are superpositional, the pressure does not seem circular anymore. Now the waves start to overlap with each other and an interference pattern emerges. If we look at the amplitude, we can see that there are some points where we have less pressure than before and some where the pressure gets higher. If we flip the phase of one speaker by 180 degrees, this means that while one speaker is pulling on the air, the other speaker is pushing. The interference pattern changes. If you look at the axis between the speakers, you will realize that you can always see the white line, as long as no wave is in front to block the view. This means that the pressure there is always zero. One step to either side and the pressure goes up and down again. But if you are exactly on the line between the speakers, there is no oscillation, and thereby no sound. This is what we call destructive interference, and it happens when two waves of identical amplitude hit each other but are shifted by 180 degrees, and thereby always point in exactly the opposite direction. Since we have a rough feeling for the way sound waves can cancel each other out in a spatial world, we will reduce our dimensions to only one. Because we don't hear everything in the room since our ear is always at exactly one position. We do not need to calculate the sound waves for every place, but only what happens to the pressure where our ear is. For now, we put the single ear in the center between the speakers. In our first example, the wave was coming from only one speaker. This would be the green wave. The yellow wave represents the sum of all waves that hit our ear. In this case there is only one, and therefore it's kinda trivial. Our eardrum would be swinging with the same respective amplitude and frequency. If the wave is at a high point, it means we have high pressure, and the air would push on your eardrum. If it is low, it would pull. In our second example, there were two speakers. The distance to both speakers is identical and they play the identical sound, and therefore we can simply add those waves together. Now in our third example, one speaker was doing the opposite of the other. Therefore one wave was flipped. I notate this with a phase of pi inside our left sign. For every non-mathematician, pi is the same as 180 degrees. If we add those flipped waves together, we see they cancel each other out perfectly. So if our ear is at this exact spot, there would be nothing we could hear. Let's say there are now two different waves, still with the same amplitude, but let's say one oscillates with 6 Hz and one with 8 Hz. Those frequencies are not audible, but it is much easier to visualize 8 oscillations per second than 440. So let's just run with me. Since the frequencies are now different, there are times when one wave is pushing while the other is pulling, and sometimes both pull and push exactly at the same time. And if we add them together, we get this weird shape. Our new signal has a special property. There is a new sine wave hidden inside. here. This purple wave is called an envelope and has exactly half the frequency of the difference of our two initial frequencies. This envelope also goes the other way around, here. But how did it get there? Let us generalize these formulas. We don't use specific frequencies, but take any frequency we can think of and call them f1 and f2. If we add two sine waves with different frequencies together, we can use the trigonometric identity called sum to product, and our summed wave can also be described as this multiplication of a sine and a cosine. Now look at this, we found where our beat frequency came from. And also there is this new term in the front, where we have f1 plus f2 divided by 2. This frequency will be called our carrier frequency, which is the average of our two initial frequencies. Therefore, if we hear the physical beat frequency, we do not perceive the initial tones as individual frequencies anymore, but as a new average frequency, with a beat on top. And honestly, I find this effect alone really fascinating already. Be careful though, because the beat frequency we see in our formula is not the same frequency you hear. We hear the loudness of the amplitude changing, which changes with double the frequency of our beat frequency, like you can see. This shape is not a sine wave, but the absolute value of a sine wave. This means negative values are flipped to be positive. So remember, the audible beat frequency and the mathematical beat frequency are not the same. You can test all of this by yourself if you want. Play two slightly different tones through one speaker and the speaker will oscillate with the carrier frequency and have the additional wobble of the beat frequency. Or use loud stereo speakers, where each plays a slightly different frequency and in the room the same effect appears, since the pressure waves now mix in the air. There is actually a well-known use case amongst musicians. You can tune instruments pretty precise by listening to the beat frequency between two strings. Try it out yourself if you want. Slightly detune one string of your guitar or violin and listen to the way the beat frequency emerges and vanishes as you tune your strings relative to another instrument. Here's a bit of skill involved since you need to bow pretty accurate, but if you listen carefully you can hear the same wobble on top of the note, if they are close. Since we now understand how a beat frequency occurs in nature, let's talk about what should happen if you listen with headphones and split the frequencies in a stereo image, because this is far from trivial. Till now, all the interference between the waves came from pressure waves or electric waves overlapping each other and cancelling each other out. But this cannot happen if both our earbuds play only one of the two frequencies. Those waves will never overlap physically, and we can prove that. This sample has left and right out of phase by 180 degrees. For reference, the same frequency but in phase. If the signals are electric waves or physical pressure waves, they would cancel each other out if they overlapped. You can check this by turning your phone speakers to mono. Explanation is in the notes. The first example will be just silence, while the second sample plays the note you heard. But if you listen with headphones in stereo, we will always hear the sound, no matter what the phase difference is. I've tried to tackle some effects of hearing phase in my first video. You can watch it if you are further interested, since those effects are obviously related but a bit different. But nevertheless, the physical interference is therefore not what creates the beat frequency. It is something else our brain does by itself, kinda like, yo, those frequencies are close, so there should be a beat, even though the fact that is necessary to physically create the beat frequency is missing. And how does our brain do it? We are not really sure, to be honest. Now, in difference to the phase video, this time there are loads of studies. It has been found that the binaural beat frequency is best heard between 1 and 30 Hz, while the acoustic beat will still be perceived as a beat frequency up to 90 Hz. While the carrier frequency for the binaural beat should be lower than 1 kHz, the acoustic carrier frequency can theoretically span the width of hearing. For me, this means it has more to do with the phase difference and spatial hearing than with actual interference, but I could be wrong though. This perception is also very personal, with some people being able to determine higher and lower beats with very different accuracies. And if you search for this effect, you will stumble upon many theories how this perception of a beat is connected to brain waves. But if we consider all the studies that have been made, there is no conclusive data yet. It is great that there are tons of studies, but most of them have really bad sample sizes, and pretty much everyone tries to measure a different variable while using different techniques to calculate a baseline, which makes all of them pretty hard to compare. And those of them who try to measure the same thing sometimes even contradict each other. So you can't expect to get any superpowers anytime soon just by blasting your brain with binaural beats. But it still kinda demonstrates the importance of huge datasets. If everyone makes a study with only 8 participants, it is just as good as no study. But if you get thousands of participants, you may even find statistical effects you weren't even looking for. That's why I encourage you in Braze's self-promotion to take a look at my short survey, which takes only 1 or 2 minutes. There I look at the perception of phase. I already told you about the video which explains it in detail. If you are interested, link below. No matter the outcome, I will use it in a future video to explain you how we can analyze the data and how to try to draw more or less reliable conclusions. In the end, I think this phenomenon is a great reminder that there are many things we do not know about ourselves. Every observation we make has to be taken with a grain of salt, and especially in the auto scenes there are loads of people who will tell you they can hear things no one else can. Then it is a good idea to take a look on the physics behind to understand if there may actually be something, and sometimes it is and sometimes it isn't. We are not foolproof. Still, musically I think this effect can be a pretty powerful tool. Even if the binaural beat frequency is a bit wonky, a casual beat frequency could maybe spice up some of your songs. I'm happy you stayed with me till the end, so here you have some cool effects and additional samples. Keep your ears curious, and till next time.